All right, good afternoon. This is June 12th, Thursday. Wow, Friday 13 is tomorrow. All the bikers in Port Dover are going to gather. So I hope we're going to have everybody in class tomorrow. Anyways, Fenchurch College, London, Ontario. The course is ELEC 1013 Network Cabling. And this is week 6 of this year. And during the week 6 of this year, this is the topics that we're going to cover. Coaxial cable, characteristic impedance, multiplexing that has to do with broadband and baseband transmissions as well. So today, I think we're going to have only time to go to the coaxial cable, and we're going to start on the characteristic impedance. So these two topics are going to be covered today. All right, let's start here. So, okay, yeah, F5 is the starting thing. All right. So coaxial cable, that's what it looks like. And if you do have internet provided by cable, so-called cable internet to your home, this is the cable that you're going to see, and the thickness of the cable is going to be most likely, if not at all cases, it's going to be RG6. R stands for radio, and G stands for guide. So radio guide. Now, the 6 has nothing to do with anything. It's just a cataloging number. As the engineers develop the cables, they would they had to name it something, and they're not going to name it like Lucy or Jackie. They're just going to number that. So that RG6 was that number 6 available in the cataloging list. Yep. Okay. Let's name it RG6. So that's we'll talk about that a little bit more. Now, the construction of a coaxial cable is we have the center core, or sometimes we call it inner core or center core. And then we have the metallic shield that also serves as another conductor, the other conductor. So it's two conductors. And the metallic shield, well, it serves as a ground reference. And it also provides shielding from the interference. And as well, provides shielding from the signal escaping the cable. Now, sometimes the shielding is more successful than others, but generally speaking, that's the idea. Right? Now, this is just a computer-generated graphics just to show things. Now, these two here are separated by a dielectric, which, well, the dielectric is an insulator. So in reality, it might look like this, the coaxial cable. Now, it is called coaxial because the center core and the outer conductor, they share the same axes. And sometimes, like this is the other view. If you're looking straight into it, that's what you would see here. Here will be the center core, dielectric, and the outer conductor or metallic shielding. It also, you might hear the term concentric cable because, well, it's both the inner conductor and the outer shield. They share the same center. They are around the same center. So, but coaxial cable is the term that is mostly used in, well, in North America. I will speak English here, so the coaxial cable, probably because it's easier to pronounce or takes less effort. But in Europe, UK, somewhere you might hear something that's concentric cable. So it's the same thing. All right. So in reality, there's a picture of that. Here's the reference. Here's the outer jacket. So it's covered by jacketing. Now, sometimes you're going to see the designation of RG, whatever number, and you're going to have a slash, and you're going to see the little letter U. The U stands for UV rated. If you see that U printed on the jacketing, That means that the cable is UV rated, which means that it can be installed outside, exposed to the sun, and it should be okay. If it doesn't have that U, which means it's not UV rated, if you install that outside without any protection from the sun or any enclosing thing, within a year, if you just grab it with your hand, you can crush it into a powder almost. Right? Talking about the jacketing. Right. So here is, well, there's a bit of a double shielding going on. The signal escaping or bleeding out, it was always a constant problem, especially, well, maybe not as much now, although still a huge part of internet providers, a huge number of internet providers, they use cable to your house. Fiber optics is becoming more and more popular. However, this thing is still going on. So, well, the protection from the interference and making sure that the signal doesn't escape, affecting other things, maybe other cables around it. It's an ongoing issue that is being addressed, and as I said, sometimes more successfully than others. In fact, well, some years ago, when the cable TV delivery by this coaxial cable was the main source of the cable TV signal to the residential and to the houses, okay, to the end clients. There would be huge networks on the utility poles and all that stuff that was going around, and that would cause a lot of signal bleeding out, because if you have a lot of them, the shielding works but doesn't work 100%. So there would be, well, at that time, like 80s, 90s, they didn't have the drones, so they would go, with helicopters or planes, and they would have some sensing or measurement measuring devices or meters to actually map out the interference caused by this cable TV signal, and you could actually see it from the air. Right? But then again, the idea is the shielding is supposed to protect from outside interference and protect the signal from affecting other things by escaping from that. Right? But the reality is what it is. Sometimes some signal does escape. So some cables may be more shielded than others, and there'll be different grading of those and different designations. In this case, we can see, well, there's that braided shielding that also serves as the other conductor, and there's a center core, and around the center core, around the dielectric here, there is also a foil shield to provide additional shielding effect here, right? So what did I say here? Coaxial cable is a two-conductor cylindrical transmission line, right? So it's a transmission line, of course, naturally, typically comprised of a center conductor, an insulating dielectric material, and an outer conductor, which also provides shielding. That's what it looks like. Right? Well, what does this slide say? What do they write here? A series of standard type of coaxial cable were specified for military uses in the form of RG, and then there's the designation number, and then with the slash and complemented with the letter U, which we already talked about. This indicates that the jacketing is UV rated. Now, those cables, they date from World War II and were listed in the publication here, published in 1962. And these are the specs. You could type that in, just point again. You could type this in Google, and you're going to see the archived specification list or document that contains specifications for different types of coaxial cables. Well, 1962. These days, some of those designations might be obsolete by now. But if you're interested, you can just take a look at some of those. Now, why was it developed? The cable mostly was developed for the radar use. Of course, the radar was a new thing during the World War II. So, well, I know two locations that during World War II the radar was developed. It was around Pearl Harbor in the States. Um, and there's a famous movie that describes the attack on Pearl Harbor when the United States joined the Second World War, and then also it was around Dover or Port Dover, but the one in England, not the one that we have here that the motorcycles go tomorrow, which is Friday the 13th. But the Dover, the shores of Dover or Port Dover in England, also they would have radar arrays pointed at the Channel La Manche or the English Channel. So that was the beginning of it. So the cables were used to link the transmitter and receiver equipment with the radar antennas. So that's why the designation stands radio guide RG. The radio signal, or well, it would be radio waves, but they would be contained within the cable. So that's a bit of a history of why this thing was developed. Now, sometimes the dielectric here, it could be some form of PVC material, and some of the larger ones, like sometimes they can go, a few inches in diameter, the whole cable. Like for example, to provide the signal for the radio stations and those huge antennas that you can still see some of those antennas. If you go Wellington Street towards St. Thomas, we're talking London, Ontario, Canada here. On the outskirts of, like, when you're leaving London, on the left side, you're going to see those huge, well, long wave antennas for the AM transmission. And those antennas are provided with the signal by a coaxial cable, but it's a huge cable. So in that case, with that size of the cable and that length, the dielectric that's used, what separates the inner core or inner conductor with the outer shield is basically air. And there are those some so-called standoff insulators just packed along the cable to just keep that thing in the center. Right? But for what we are going to mostly use, although I shouldn't be saying that, because what if you get a job at the radio station, then you'll be dealing with that bigger cable, but then again, you're going to have to study that particular cable and its characteristics. All right. Now, as far as the size, this is not to scale, but roughly it's a comparison between the sizes of the diameters of the different cables. So here's RG6 compared to RG11 and RG59. This one here, it's for us, it's easier to imagine because, as I said, this is basically the type of a cable that if you get the internet provided to your house, it would be by the cable of that size, which is slightly smaller diameter than pinky, right? So then we have different designations. The cables display different characteristics and different specifications, and we're going to take a look at some of those right now. Now, actually, not yet. All right. I need to cover the topic of something that's called a characteristic impedance. But in order for us to understand what characteristic impedance is, we need to take a closer look at what actually impedance is. So we're going to talk about the impedance versus characteristic impedance, or vice versa. All right. So let's take a look at some of the details when it comes to this topic. Also, I'm going to say that well, this information that I'm going to give you right now, it might overlap with some other subjects, or in better terms, if I could say that, it might help you with understanding some of the concepts that will be presented to you in other subjects. So I would just say, just pay close attention to that, because this is a actually valuable lesson for you right now. All right, so let's take a look at something that's called a resistor. All right. A resistor, we consider that as non-reactive component, right? Because its resistance remains unchanged even if the applied frequency increases or decreases. So it doesn't matter what the frequency you apply to resistor. A 100 ohm resistor, for example, is going to have 100 ohm resistance, or the opposition to the current flow, with the value of 100 ohms, whether you apply a DC signal to it or power, or if you apply the power in the form of alternating current or AC. And if you change the frequency of the alternating current of AC frequency, the resistor still will have the unchanged value of its nominal value, like for example, 100 ohms. Okay? All right, so that's a non-reactive component in this type of in this way of understanding that in this perspective that we're talking about here. Okay, now capacitor and inductor, these are two interesting animals here that we're dealing with. Now, capacitor is a reactive component, and so is inductor, or a coil, or a solenoid. Is a reactive component because it's, and I put the resistance in quotes. So let's just take a look at this sentence here. Capacitor is a reactive component because its resistance value changes if the applied frequency changes. So depending on the frequency, whether it's higher or lower, capacitor will give you different opposition to the current flow. It's going to have different resistance. Now, same thing with the coil or inductor. Is a reactive component because its resistance value, same thing. They just work a little bit different. They kind of work in opposition to each other, but the way they react is pretty much the same, or the same but different, and we'll talk about that. Because the resistance of a non-linear, and I know some people might want to give me a hard time about that non-linearity concept that I'm using here, but I just want you to know, like for example, here, there's my board. Here's my board. Let's say here is y-axis, here is x-axis, right? Y and X. And whatever the values of the X, it could be, it doesn't matter what we are presenting, but X but the relationship between X and Y, if it's a straight line, it is going to be a linear type of a relationship. If we have something like this, then the relationship between the X and Y is non-linear. Yes, I understand that concept, so don't worry. Whoever wants to hang me on that. But what I mean by that non-linearity is, maybe I should remove that, just not to cause any frictions within the world of science. But let's just take a look at this concept here. Because the resistance of a, reactive component, should probably say, is affected by the frequency changes, then we can say that the capacitor or an inductor has a reactive resistance. It doesn't have the constant resistance. The resistance changes depending on the frequency that the part is exposed to, and it's going to give us different resistance depending on different frequency. So we call that reactive resistance, and in short, the term is used, we call it reactance. So that's why I put the resistance in quotes here, because it's actually reactance. Now, let's take a look at a couple of the formulas here. The reactive resistance or reactance is expressed by the letter X. Now we see XC and XL. XC, it's a capacitive reactance that the capacitor is going to give us. And of course, the XL stands for the inductive reactance. Now, here's the formula. They work, as I say, they work the same but different. The reactions are similar, but the directions are different. It reacts the opposite. They react opposite to each other, but they react the same as the conceptual understanding of it. So, capacitive reactance. Here's the formula for that. Yeah. Equals 1 over 2 pi Fc. Now, F is the frequency that the part is exposed to, and C stands for the capacitance. And in this here, the other formula, the inductive reactance, is expressed by this formula. Same thing, but there's no 1 over that. So it's just kind of opposite. And so 2 pi, 2 pi, what 2 is, it's 2. Pi is the 3.14 and forever. And here's the frequency and here's the inductance. Now, the capacitance is expressed in farads, right? Microfarads, picofarads, nanofarads. And it has something to do with the last name of a person who introduced the word to the extensive studies a couple hundred years ago. All right. Now, then here's the inductance, and the inductance is expressed in Henrys. Right? And again, it's to celebrate the person who played with that and introduced the word to this. Yeah? And of course, the frequency is expressed in hertz. Okay. Now, hertz also is a last name, and I need to make a point. I have to make a point every year, just so we use the terminology correctly. We have 100 hertz, we have 50 hertz, we have million hertz, we have 2 hertz, and we have 1 hertz. I'm saying that because sometimes I hear people saying 1 hertz. Okay, no, hertz is not a thing. It's a last name, so it will be 1 hertz. Okay? All right, let's keep going. Now let's take a look at the concept of impedance. Yeah. Consider a non-reactive component such as resistor. Changes of the frequency of the source do not affect the resistance. We already covered that. The resistor will oppose the current flow in the same way, no matter the frequency. So here is the here's the alternating current power supply, AC power supply, and of course it changes its polarity with whatever frequency. How fast it changes, the frequency will determine that. And whatever the resistance of that thing is, it will remain constant. Now, let's see something that's like a reactive component, such as capacitor, right here. To a pure DC source, the capacitor acts as an extremely high resistor. Pure DC source. Now, I'm going to digress a little bit because I just have to, okay? Just so we understand things. So we're on the same page. All right, here is X and Y axes. Here's the time, and here's the value of whatever it is, let's say voltage. And here's the 0, here's the plus sign side of it, and here's the minus side of the Y axis. If we have the polarity of the power supply goes plus to minus, plus to minus, plus to minus, okay, it just keeps going. And if we just apply it to the time, if we're just moving that way, plus and minus, and we move around the time, we're going to have something that looks like a sine wave, all right? So it's going to look like this here and here. We just go up and down and moving along the timeline, okay? And keep going forever. So this is called AC, alternating current, because the polarities do change. Now, let's see here. If we have that going on, is this an AC? Well, yes and no. Yes, it's because it's not constant. But is it considered technically AC? No, because the terminals do not change the polarity. They might have higher or lower value, but they still remain on the plus side. Or, as a matter of fact, it could be on the left, on the bottom side. But the terminals do not cross the zero line. And sometimes we could call it a pulsating DC, because the current flows in the same way always. It's just sometimes more and less, sometimes more, sometimes less. So that's DC. But why could it be called AC? Because it could be, let's say here's the middle of that waveform. It could be the AC component sitting on or riding on certain DC value. Right? So make of that what you will. Now, here's AC. If we do add the waves, okay, we're going to have a couple of waves going here and maybe some other frequencies going here. If you keep adding those, and if you pack those frequencies so tight that not even a church mouse can go through, eventually you're going to end up with a straight line somewhere there. I'm just going to leave you with that. Okay, let's go back from this digression here. So capacitive reactive components is a capacitor due to a pure DC source. I hope I didn't confuse you with that concept that I just showed you. But let's say a DC source, let's say it's a straight line. Right? Let's say we got a straight line going on here. Oops. There's X and Y axes here. Boom, boom. And here's, let's say, 10 volts. So here's the voltage, here's the time. And let's say that we have a flat line going right at, we always have 10 volts here. So that's a DC. Now, to a pure DC source, if it was a pure DC, not the little tilde wavy thing, it's just a plus and minus, the capacitor acts as extremely high resistor. It's just like disconnecting, having two loose wires, just like that, right? Excuse me. All right. Now, I'm just going to stop on this line and go visit the same line on the inductor side. To a pure DC source, the inductor acts as an extremely low resistor. It's just like if you were connecting those two sides with a piece of wire, which is, for the most part, we can consider this thing as 0 ohms, unless you want to go into really highly scientific details that, yes, you will have a little resistance, but we're not talking about that at this point. Okay? So, to a capacitor, to DC, capacitor acts as an open circuit. And to DC, to pure DC, coil or inductor acts as a straight piece of wire, just like a short. All right. That's why we like to combine circuits with, we like to add resistors to things, so to slow down the current, so we don't have a boom going on and blowing the fuses. Right? Now, as the frequency, let's look at the capacitor again here, okay? As the frequency of the source increases because, well, when it comes to the AC or DC, then this is considered as 0 hertz. All right. Oh, okay. Excuse me. Sensitive microphone. All right. Anyways, so when things start moving up and down, that means we're applying some sort of frequency here. Now, it could be a low frequency, or it could be high frequency. Right? As soon as we have that, then the capacitor starts behaving a little bit different. As soon as we start introducing a frequency to a capacitor, it begins to conduct. The higher the frequency, the less resistance the capacitor is going to give us. To the point that if it's an extremely high frequency, then the capacitor is going to conduct as if it were just a straight piece of wire. How does it work? How does that work? Well, when we have a, well, let's just say we have terminals plus, minus, let's say we have 10 volts. Okay. And we have this connected to a, well, let's see here. Let's just be proper here, okay? So add a resistor prophylactically, and let's put a capacitor in the circuit. Yeah, all right. Now, the resistor is just so we can limit the current a little bit. So things are happening in a controllable way instead of going haywire, just, whoa, let's have all the current at once, because that would kind of be no good. So now, when the current starts flowing, and let's consider the conventional current flow. So the current is going to flow from plus to minus. Then you're going to have accommodated charges, because let's say this capacitor is completely discharged, neutral. Then we're going to have some charges building up here. Let's just we're going to get some positive charges accumulating here. We're going to have some negative charges gathering up here. They can't cross the line. They can't cross it because those two plates, consists of two plates, separated by, well, dielectric, which is insulator. So nothing can cross. So they're just going to gather up here, and just going to gather up here, and as they keep charging. So at the initial stage, if the capacitor is discharged, there's going to be huge inrush of the current because the capacitor is hungry for charges. So there's going to be place to put them in. So they will try to get there, but they won't be able to. So they're just going to be standing on the border looking at each other. Right? So in the beginning, there's a huge inrush of current as the capacitor charges. And then as the capacitor keeps charging, then it's going to be less and less and less of the current flowing, because it only can take so many positive charges here and so many negative charges here. And as it fills up its capacity, capacity, then it's going to stop conducting because it's going to saturate. It's going to be full of charges, and it will accept no more, which means the current is going to go less and less and less and less. But then again, it's just like having a broken connection here. The voltage here is going to be equal to the voltage here. So because of the inrush current, initially, when there's a maximum current flow, just like a piece of wire, then of course the voltage between here and here would be 0. And as the capacitor charges, there is less and less current flow. It charges up, then the voltage is going to equalize with this point is going to be equal to this point, and this point is going to be equal to this point, because there's no current flow. Doesn't matter if the resistor is here. if the current was flowing, then another resistor, yes, there will be a different voltage. But if this thing is open, this voltage here, there's no current flow, this voltage and this voltage will be equal to each other. So we could say that in the capacitor, in a capacitor, current is first, and the voltage, we can express that with E, is second. In the capacitor, current goes first, voltage appears later. Now, if we substitute the capacitor with the inductor, so let's say instead of capacitor, we will have a coil. Let's just imagine that this is plugged in instead of that. Well, maybe I should just draw it here. It's a coil, poorly drawn coil. So here's L for coil, here's C for capacitor, and let's just imagine that this thing is broken here, and we have the capacitor or the coil connected here. So now we have that. All right, so to a pure DC, as we apply it, that is going to not conduct at all. You know why? Because as opposed to the capacitors, capacitors love change. Frequency is things are changing. Coils, on the other hand, they do not like, they despise change. They just don't want any changes happening. And coil can be compared to a spring. Let's say you have a spring, here's a wall, and you have some kind of a spring, physical spring, mounted on the wall like that. And then if you're standing here, and if you push with your hand, if you push that spring, it is going to push back on you. That means the coil doesn't like change. It wants to remain where it is. Okay. All right. Yeah. So that means coils do not like change. Same thing with electricity. They do not like sudden change. So if you suddenly apply the voltage, that thing's going to say, no, I'm not conducting. I'm staying the way I am, you know. But then if you do not change, if you just apply it, so from zero volts, you're going to go boom into 10 volts. But if you stay that way, then the coil is going to say, okay, right, there's no more changes, so we are remaining constant here. So if you don't change, I'm going to play along. So I'm going to start conducting. So, sorry, just touched my microphone. So what happens in this case, we get a complete opposite of what's happening in the capacitor, which means within the coil, because it opposes right away, so it's going to act as a huge resistor. So here's the coil side of it, which means if it acts as a resistor, it's just like as if this was broken. There was nothing in here. So you're going to have voltage first. And then you're going to have current. How? It's because first it opposes and then it lets go. So the current's beginning to flow. Here's the acronym. Eli the Iceman. In capacitor, there's current first, then there's voltage. In inductor, in coil, there's voltage first, and then there's current. You might want to remember this acronym here if you want. That's the old famous acronym, Eli the Iceman. Okay? However, I would rather you understand that you understand. I would rather have the situation that you understand the concept, and then you can go, oh yeah, I can remember the acronym. Because if I only give you the acronyms, there's so many things, so many principles, and so many concepts, and every single one of them has an acronym. Then you're going to run out of memory trying to remember the acronyms. I would rather have you understand that. Okay. All right. So that's how things are happening. We're trying to get the topic of impedance here. All right. I multi-simmed it. You can draw that in multi-sim if you want. Because I think I lost the file somewhere. So here's the power supply. Here's a switch. Resistor, 1 kilo, just to slow down the current a little bit so things are not happening in a crazy way. And just so you know, in the multi-sim, this here is called a current probe. If you don't know how to get it, just look at some YouTube shorts. Within 10 seconds, you will know how to apply current probe, because oscilloscope doesn't display current. You know, it only displays voltage. So we need to trick the oscilloscope to kind of display us something that is related to current instead of voltage. So it's called current probe. And here's the capacitor. That's it. Look what's happening. I got the magnification on the next slide here. It's the same thing. I just magnified this part. So in the capacitor, here's the power supply. What's happening? So I decided to use a square wave because I just want to have that sudden change. So what happens there? And there's the current. And here is the voltage. So look, nothing happens. So nobody expects anything. And bam, there's a change. Whoa, all right. So the capacitor says, oh, I love it. I'm going to conduct. I'm going to respond. I'm going to conduct the current. Whoa, just inrush the current. But then the plates are charging. So the current is becoming less and less and less. So naturally, the voltage is going to start slowly appearing there. So that's how capacitor works. Now, coil, inductor, different story. I just magnified this part here. Here's the power supply, and here's the sudden change. Boom, right? Nothing expected. Nobody expects anything here. So coil says, just minding its own business, and bam, somebody just applies voltage to it. And he says, no. The coil says, no, I don't want to conduct. I don't want to change. So it gives us that's the voltage across the coil. It shoots up the voltage. Voltage appears because it doesn't conduct. It just tries to stop anything from change. So it's just like opening the circuit. So of course, yeah, we're going to have the voltage on these 2 points. So look at that here. Boom, the voltage appears. But then as if after the change, you stay constant. It says, okay, I see no change. I like it. So I'm going to kind of respond to it, give you, start conducting current. So the voltage is going to disappear from that again, and the current is going to start flowing again. Or flowing at all. So then these are the two. You can download the presentation that's already, I think I already posted that in our lecture notes. These are the two side by side. Here is an interesting concept. It's called a resonance. I'll come back to that. Look, there's another multi-sim I did. I put the oscilloscope, but I put a reference between those two. Here is a capacitor, here's a coil, and right in the middle, I put the reference, like the ground of the oscilloscope, or the reference, not the ground, but the reference, the zero reference. Look what's happening. Because the opposite, they act is in opposite to each other, then the voltages are going to be in opposite to each other. Now, depending on the values of the capacitor, this might be bigger, this might be smaller, or vice versa. But the phase is going to be 180 degrees out of phase. See, they're like almost like mirror image. Okay. Well, what is associated with voltage? The more resistance you have, the more voltage you're going to have that across the resistance if you have two resistors in series. And then one of the resistors is going to, if it's a bigger resistor, then it's going to have more voltage than the other smaller resistor if you have them in series. Okay. So resistance goes together with voltage. Okay. Let's take a look at this here now. Here is the zero reference, pure resistance. Why do we have pure resistance? Because all components, or maybe there's that resistor that is in the circuit that we drew in series with all this stuff. So we're all analyzing the whole thing now, the whole circuit. So here's the resistance value. And the resistance value is going to be at the angle of 0 here because it remains constant. So it's going to be voltage and and current in at the resistor. They're in phase. The resistance has a 0 reference angle. Now, because in coil, the voltage happens first, and in capacitor, the current happens first. So the current and voltage are in phase within the resistor. So here's the current. Then because the current happens and the voltage happens a second, then the reactance or its resistance is going to become second. So first and second, okay? Now, so the inductive reactance is ahead of the resistance, pure resistance, and the inductive reactant, capacitive reactance is second to the current. You might want to go back to as I was explaining how things are happening with the oscilloscope, the coil, and capacitor connected to a circuit. Well, so we have this kind of graph. Now, if we have different components, we have the series okay, so we have a power supply and the resistor and the capacitor and the coil all in one circuit. Or maybe there should be other things, connected to it. Things are going to happen and give us a total load. So in case where the reactive resistance according to the frequency is bigger than the capacitive reactance, then we just take that and put it here, and it's going to make that much smaller. And if you draw a line here and have that point here, make a point, draw that hypotenuse here. That is going to be the magnitude of the impedance. And impedance is going to have an angle right now. It's not going to be at 0 angle. In this case, because the inductive reactance is bigger than the capacitive reactance, then we can say that this load totally is inductive. Most of the houses will have inductive load because there are lots of transformers being plugged into the hydro outlets. And if the capacitive reactance is bigger, then we take that one and put it there and make it that much smaller. So this here, this length between here and here is that length here. And then if you draw it, Here's the magnitude, but it's going to have of the impedance, but it's going to have a different, what do you call it? Angle. Okay. Now, if you have to go to another class, please go. I'm just going to keep going for maybe a couple more minutes, and then you can catch it later on YouTube. I know we're running out of time here for the class here. And now, how do we calculate that? Here's a guy named Pythagoras that calculated the pyramids and all that stuff. So here's the Pythagorean theorem, all right? So that's how you can also use trigonometry to calculate those. You can either way. So what's impedance? Impedance is the combination of the resistance, capacitive reactance, and the inductive reactance, as you can see here. Right? Now, because of resistance, things have anything, I will have conductance because it's opposite to resistance. If it's capacitive reactance, it's going to have capacitance, and so on. I just put those things there. Now, you can see here RG58 uses a different designation than RG6. It's a different cable. I just put that thing there. I'm gonna finish on this concept here. Erase that. All right, so let's say we have and that is going to be repeated just to kind of enforce the knowledge or the retention. If we have a cable, coaxial cable, like this here, and here's the center conductor, and here's the cable, keeps going. Let's finish that, and it just goes like that, right? Now, if we drilled a hole in the middle of that, there's a highly hypothetical situation. And over here inside, we have that inner core that's going inside. And if we run a wire and connected that to the inner conductor, center conductor, and the other wire we connect to the outside conductor, the outer conductor, what we have done is we just made a capacitor out of it. Right? We have two plates of certain size separated by a certain distance. So what is capacitance depending on? Well, the capacitance depends on the size of the plates and the distance between them. But now, if we increase the total length of the cable, it's just like increasing the size of the plates. So the capacitance is going to change, which means that its reactance is going to change, which means the impedance is going to change. But we are not using cables like this, are we? What happens is that we need to know, because how is it that the amplifier, RF amplifier, for example, which stands for radio frequency amplifier, it is going to insert a wave into this cable. How is it that the amplifier introduces a wave into a cable? Well, it takes a wave, throws it in there, and that's it. Once the wave is thrown into the cable, it's there on its own. It's going to travel along the cable until it becomes so weak that it's going to stop existing. And then it's going to throw another wave, and the same thing is going to happen. Just like if you have water and here's the bottom of the lake, and you drop a stone here, the stone is going to hit the surface of the water. It's going to make waves going in all directions, and then it's going to hit the bottom, and it's going to be completely out of the picture, not connected to the whole system, but the waves still continue on the surface of the water, right? Right. So it's the same thing with the electrical signal, electromagnetic wave, boom, inserted into the cable. All right. Here's the concept of impedances. The amplifier is going to have certain output impedance. And the whatever that thing is connected to, let's say the cable, for example, it is going to have the input impedance. But it's not the total impedance. See, what we need to understand is the amplifier doesn't care about the total length of the cable. Just like that little rock doesn't care how big the lake is, it just cares about what happens here. So at the time that it hits the surface of the water. So here's the same thing. The amplifier doesn't care about the total length of the cable. The amplifier only cares about how hard or how easy it is to insert a wave into this cable. We need to match the impedances. The output of the impedance of the amplifier, the output impedance of the amplifier has to be equal to the input impedance of whatever it is, for example, this cable here. In this case, we can achieve something that's called a maximum power transfer. All the power is going to smoothly be transferred from one thing to the other. And that's all the amplifier cares about. If the impedances are mismatched, then not all the power is going to get through. Some of them is going to bounce back, come back to the amplifier, heat that amplifier up, and so on. Usually that it happens like that. Well, so looking at this concept, we need to have some other terminology. We need to understand other things. So how do we kind of have the impedance here, length of the cable, that thing doesn't apply, it doesn't care? Well, we have something that's called characteristic impedance. And the characteristic impedance is going to be used to determine if this here is equal to this here. That way, if they are equal, then we can have the maximum power transfer, and then it's going to travel. So the length of the cable doesn't matter. The characteristic impedance here's the formula for that. Look at the formula here. Here's a coaxial cable. Here's the diameter of the inner core, of the inner conductor. Here's the diameter of the outer conductor. And they are plugged in right here. And there's some, mysterious log thing here. That's for logarithm. It's a log. And there's that mysterious 138. Don't care about that right now, but it's there. And there's a square root of K. What's K? Relative permittivity of the insulation between the conductors. Here I explain the permittivity and relative permittivity. In our case here, in this case, is the resistance to the electric field, and relative permittivity is the permittivity of the material compared to the permittivity of vacuum. All right, so what I'm trying to say here, nowhere in this formula is the total length of the cable plugged in, right? So the characteristic impedance does not depend on the total length of the cable. It depends on these. And usually you can compare it to the total impedance of the first meter of the cable. Or in some sources, they will give you the total impedance of the first foot of the cable. Yeah, so it's just the impedance of whatever is at the beginning of the cable. And that's the formula here. So the characteristic impedance does not depend on the total length of the cable. Why do we need to know the characteristic impedance? It's because we need to match that with the output impedance of the source of, in this case, amplifier, in order to accomplish maximum power transfer. All right. So that's it for today. I think you got a little bit of a red pill from the matrix thing, which is good. And next time we see each other is going to be in person. However, the other group had the second part already on YouTube, so all of those classes you'll be able to revisit one way or another. So next time we see each other, which is tomorrow, this is the class of 2025. We're going to talk about the other topics that we have mentioned at the beginning of here. So we're going to cover the coaxial cable. We're going to talk more a bit about coaxial cable next time, and then we're going to cover the idea of multiplexing, broadband, and baseband. But that's it for today, ladies and gentlemen. Have a wonderful day.